Hello, everyone. Good morning. Good morning. Yeah, first of all, I would like to apologize for the mistakes in question 4 during the exam. Yeah, sorry that it would have created a lot of troubles for you. And now, yeah, welcome here. And then let's start with the exam 2 solution. Okay. Eh, let me start with the screenshot. Let me see. Okay. So let's start now. So the first question is an exercise question. It is appearing also in last year's exam. So a similar flavor appears in last year's exam. We have this recurrence relation. An is equal to 6 times an minus 1 minus 9 times an minus 2. And then we know that a0 is equal to 1 and then a1 is equal to 9. This question asks us to show, using induction, that an is equal to 1 plus 2 times n multiplied by 3 to the power n for n is greater than or equal to 0. Okay, so how can we show this? So in this example, we have actually two initial conditions. So what we want to show is, first, verify that these two initial conditions satisfy this formula. So we can easily check whether a0 is equal to 1 by using this formula. So to compute a0 using the formula here, so first of all, we only know a0 is 1. We don't know a0 should satisfy this one. So what we are now trying to do is to check whether this is going to give us 1 when n plugs in to be 0. So when n is equal to 0, 1 plus 0 times 3 to the power 0 is actually equal to 1. So this formula works for n is equal to 0. And also, let us track what happens when n is equal to 1. So when n is equal to 1, we will get 1 plus 2 multiplied by 3. So it is going to be 1 plus 2, which is 3. 3 times 3 is equal to 9. So this formula also works when n is equal to 1. So these two forms the base cases for this induction process. Okay? And now we want to check. So what we know here is we know that the relationship between an and an minus 1, an minus 2 is like this. And we want to show that this formula continues to work when n is equal to 2, 3, 4, 5, 6, and so on and so forth. So what should we do? Okay, so let us suppose that, so we are going to try the inductive case. So we are assuming that the formula is true for all n is equal to 0, 1, 2, 3 up to k. So as far as we know, k can be equal to 1 now. Yeah, because we know that it is true for n is equal to 0 and 1, right? So assume that it is true for all n is equal to 0, 1, 2, 3 up to k. And then we are testing whether the formula is also true when n is equal to k plus 1. Now when n is equal to k plus 1, what do we know? So we copy what we have here when n is equal to k plus 1. So we have ak plus 1. It is always equal to 6 times ak minus 9 times ak minus 1. So we copy this. This is always true. And now the next part here is we are having this assumption, this inductive assumption. So we can now, based on this assumption, to plug in the value for ak now. So ak should be equal to 1 plus 2k times 3 to the power k. And then we also want to plug in the value for ak minus 1 here, so which is equal to 1 plus 2 times k minus 1 multiplied with 3 to the power k minus 1. So after some algebra process, we have this one, and then this one, and finally we have this one. And then what we have just shown, we have just shown that the formula, so this is exactly what the formula is saying. The formula also works when n is equal to k plus 1. So altogether, we now have the base cases and also the inductive case. And we have shown that these two are both correct. So by using the principle of mathematical induction, the formula is correct for all n equals to 0, 1, 2, 3 up to infinity. And notice that this is so here we need to have two base cases here, and also we need to use strong induction, yeah, because we need not just AK to be correct when we are showing AK plus 1 is also okay. We need both AK and AK minus 1. So these are two minor things that we need to be careful. Okay, let's start with the next question. So the next question is, we have R red balls, G green balls, and B blue balls. Altogether, there are three distinct boxes. We want to find out how many ways can we do to distribute all the balls into the boxes. Now, because the boxes are distinct, yeah, but the balls are identical. So in that case, to find out how many ways to do so, actually, we first observe that the process of distribution of red balls is independent of the process of distributing the green balls and also the process of distributing the blue balls. So we can actually use rule of product to help us to solve this question. We just find out what is going on about the red balls. And then we find out what is going on about the distribution of green balls. And then we find out what is going on about the distribution of the blue balls. So the total number of ways is equal to the number of ways to distribute red balls multiplied with the number of ways to distribute green balls and multiplied with the number of ways to distribute blue balls. And it turns out that the number of ways to distribute red balls is just to find out how many ways can we have three non-negative numbers adding up to R. Yeah, because we need to specify how many balls, how many red balls in the first box, how many red balls in the second one, and how many red balls in the third one. So it turns out that this is the value. CR plus 2 choose 2, or CR plus 2 choose R. They are the same, right? And then this is the case for distribution of red, and then we multiplied it with the cases for distribution of green balls, and then multiply this with the distribution of blue balls. Okay, so this is the first part. Now the second part, we have an extra constraint, we have an extra restriction. We require that none of the boxes will be empty. So we have this new restriction. So how many ways to distribute all balls into the boxes? So how can we solve it? Okay. So we can solve it by count out all the possible cases one by one, of course, cleverly. Actually, what we are going to do here is that we have already solved the first part. So this is without any restriction. So what we need to do here is that we need to take away those cases that does not follow the restriction. So we should take out the cases where we have some empty boxes. Okay, so how can we solve this? Let me use N1 to denote the number of ways that only box 1 is empty, but box 2 and box 3 are non-empty. And then I use N12 to represent the number of ways that only box 1 and box 2 are empty, where box 3 must be non-empty. So first of all, we know that N12 is equal to 1 because it means that all the balls are now in box 3. And the total number of ways will be equal to what? Here, it is the previous answer, right? But then we should do what? We should minus the case where box 1 is empty, exactly box 1 is empty. Also, we should minus the case where box 2 is empty, and the case where box 3 is empty, and the case where box 1, 2 is empty, and the case where box 2, 3 are empty, and the case where box 1, 3 are empty. So we should do this. But things are quite symmetric. So the number of ways that only box 1 is empty is the same as the number of ways that only box 2 is empty, and it is the same as the number of ways that only box 3 is empty. So what we need to do here is that from the desired answer, we should deduct from the previous answer 3 times m1. And similarly, we should also deduct it by 3 times m12. So this minus 3 here. So what remains is to find out what is the value of n1. So if we know n1, then we are done. So what is n1? So n1 is the number of ways that only box 1 is empty. So Let us compute the case that box 1 is empty, but we don't care about box 2, box 3. So the number of ways that exactly box 1 is empty is r plus 1 times g plus 1 times b plus 1, because for the red balls, we must distribute it into the box 2 or box 3, so there are r plus 1 ways of doing so. 0r and then 1r minus 1 and so on and so forth to r0. Okay, so there are r plus 1 ways. So we have, this is the total number of ways that box 1 is empty, but this is not the case that only box 1 is empty. So this is box 1 is empty. And this is overcounting a little bit. We have overcounted the case that it is not only box 1 is empty, but there may be another empty box. So we should minus n12, and we should also minus n13, because these two cases are now counted here, but that should not be counted. So it's r plus 1, g plus 1, b plus 1 multiplied together minus 2. Is that okay? So if we combine with the previous formula, so we now have n1, the value of n1. So it is going to be minus 3 times n1. 3 times n1 is equal to this one. And then finally, we should minus 3 times n1 too, so which is equal to minus 3. Okay, so this is one way of solving this problem. But if you have already known the principle of inclusion and exclusion, it is actually taught, okay, in the new set of slides when we talk about set. Then you could have an easier life. Now notice that for this question, we do not assume that you have already known some extra knowledge. But it is perfectly okay if you use the extra knowledge to help you to solve this problem. Is that okay? So as long as your solution is clear enough, that will be fine. So what we want to do here is that we are applying inclusion-exclusion principle. So we define something that is similar as before. We have M1 here. This time, M1 just requires box 1 to be empty. It doesn't doesn't care whether box 2 or box 3 whether they are empty or not. And then M12 just require that box 1 and box 2 are empty, and it doesn't care about whether box 3 is empty or not. We compute the number of ways of doing box 1 is empty, which we have already explained. It is equal to r plus 1 times g plus 1 times b plus 1. And then we compute the number of ways that M12, okay, which is box 1 and box 2 are empty. It is the same as before M12, which is equal to 1. And then the desired answer can be computed by, so this is neither we have any restriction. So this is the total number of ways to distribute all the balls. But inclusion-exclusion principle tells us that we should minus the ways that box 1 is empty, minus the way that box 2 is empty, minus the way that box 3 is empty. So we are going to minus 3 times M1. But here we are over deducting, so we should add back some. We should add back the case that box 1, 2 are empty, add back the case that box 2, 3 are empty, and add back the case that box 1, 3 are empty. So we will be adding 3 times M1, 2. And then after doing the simplification of the terms, then we will see that we will arrive at the same answer as here, as before. Okay, so just check. So this is going to be the original answer minus 3 times M1 plus 3. Okay, minus 3 times M1 plus 3. Okay, so that's it. So this is question 2b. Next, let us consider question 3. Question 3 is just a modification of one of the exercises that we have seen before. We want to select 5 numbers from 1 to 100, but we require that any 2 numbers must differ by at least 10. Okay, so there must be at least, they are differed by at least 10. Okay, so we want to find out how many ways are there to select the numbers. Okay, so here we use this to have a scenario like this. So suppose that we are going to select 5 numbers from 1 to 100. So let's say we use the orange ball to represent the numbers that we are selecting. So when we are selecting 5 numbers, it will create 6 groups of numbers that are not selected. Some of the groups here, for instance, this group could be containing no numbers. But what we know here is that there are going to be at most 6 groups. And then we call this group 0, group 1, group 2, group 3, group 4, group 5, something like this. Okay. And now, to analyze the number of ways to select 5 numbers, let us use UVWXYZ to represent the sizes of these groups from left to right. So let's say this group has U numbers inside, this group has V numbers inside, this group has W numbers inside, X, Y, and Z. What we need to have, we need to have these two numbers to be divided by at least 10. So that means that in between, there are going to be there are going to be 10 or 9 numbers. I don't know. Yeah, let me see. So suppose that I'm selecting 1, I'm selecting 11. Oh, so in between, there should be 9 numbers. Is that okay? In between here, there should be 9 numbers. In between here, there should be 9 numbers, and 9 numbers, and 9 numbers here. Okay, and 9 numbers here. But then there is no restriction here, and there is also no restriction here. Okay, so in that sense, we can change it to a problem like this. So there are some mistakes here, but the basic idea is the same. Okay, we will need to have u plus v plus w plus x plus y plus z is equal to 95. The reason is that we have 100 numbers in total, but we are taking away 5 of them. So in that case, we should the u, v, w, x, y, z should add up to 95. And then we have the first group and the last group. We don't have any restriction of the total number of numbers inside. So u and z is at least 0. We just need to have this one. But then for the in between, v, w, x, y. So sorry that there is a mistake here. So for v, w, x, y, any one of them should have at least 9 numbers here. So as long as there are 9 numbers here, then we can have this one and this number, the absolute value will be divided by at least 10. Is that okay? So imagine this is, let's say this is 1, and let's say this is 11. So we will have 2, 3, 4, 5, 6, 7, 8, 9, 10 inside. So there are 9 numbers. This is the minimum. So in that sense, it is greater than or equal to 9. Oh, let me quickly change it now so that, so if this is 9, then what will happen? So in that case, it is going to be, so if we take away this v, w, x, y, the 9 numbers, we have already assigned 9 numbers there. So there are going to be 36 numbers, and then there are going to be 59. Am I correct? Let me see. 36. So we are taking away 36 numbers, and then we have 95 numbers in total, and then we are taking away 36. So how many do we have? We should have 59 numbers. Am I correct? Is that correct? 59. Okay. But then 59 numbers plus 1, 2, 3, 4, 5. So okay, so it should be 64. Sorry. Okay. So after doing some calculation, then we should have this one. Yeah, let me. Okay. Is that okay? So maybe yeah. So this is the whole idea. So basically, to solve this question, it applies something that we have already studied. So the numbers here may not be exactly correct. So, but I believe they are now correct. Okay. So go home and verify it by yourself. Now we come to our problematic question that we have errors. Okay. So here this is the correct version. So we want to sum up for every k between 0 to n, where L is between 0 to up to n minus k, the value of n choose k, n choose L, and n choose n minus k minus L. So what is the follows the value of this sum? We can actually use a combinatorial argument to see that this is exactly equal to 3n choose n. Okay. The reason is that you can imagine that we have three groups of students. So let's say we have the group of student in year 1, the group of student in year 2, group of student in year 3. Altogether, there are 3n of them, and then each group there are n of them. We want to select a total of n people from these 3n people. So how can we do? So one particular way is to select some k number of people from the first group, and then select some l number of people from the second group, and then finally select the remaining people from the last group. So we have any choice of k here, but then l, we should not be considering all the cases. We can select starting from 0 up to n minus k, right? And then for the last group, it is just the remaining people that we have. So we have remaining n people, but then we need to select how many? N minus k minus l. So using a combinatorial argument, we will see that this sum is exactly 3n choose n. So in that case, if you can explain why this is correct, then you can solve this problem, and then you can also find out what is the value of n of this one when n is equal to 5. This is just a simple calculation. Okay, now how about this one? This is the wrong formula that we have posted in the exam. So what will happen for this one? Okay, now if we look at this one, so that when we fix a certain k, let's say k is equal to 1, L will be starting from n minus k, so n minus 1 here. So for the first term of L that we choose, n minus k minus L will be equal to 0. So it is still okay. So this is going to be a valid term. So it is going to be n choose k multiplied with n choose n minus k and multiplied with n choose 0. So it is 1. But how about the next term? So let's say k is equal to 1, but then L this time is not just n minus 1. So when L is equal to n, then what will happen? Then this part, n minus k minus L, will be a negative value, a negative integer. So we have not defined what is meant by n choose a negative integer, but in the literature, in somewhere else, it is common to, or it also makes sense, it is perfectly okay to say that this is equal to 0. So if we assume that this is equal to 0, then we will see that n choose k, n choose L will only exist when L is equal to n minus k. For all the other cases, when L is slightly larger, then this term will be 0. Then we are not going to add this anymore. So if we are given this formula, the interpretation will be it is going to be summing up all the cases where L is exactly n minus k. So it is summing up n choose k, n choose n minus k. And the other part here, corresponding to this, will be n choose 0, which is equal to 1. And in such a case, then this is the Vandermon's identity. So this is going to be 2n choose n. So you can also argue this with the combinatorial argument. So I want to apologize again for the mistake here. And then, so for this question, if you somehow give 2n choose n, you will have marks. But then, since we have already made the announcement early enough, I believe, and then, so as you can see from the latest announcement in the discussion board, I have tried to explain the reason why we want to keep the score distribution. So if you have any further comments, please let me know. Okay. Now finally, question 5. Question 5 is we have 12 dots, and they are located on a 3x4 grid. So there are points on this grid, and then we want to separate them using straight line cuts. So we want to show that 5 cuts are needed. So in A part, we asked you to show how we can separate them using 5 cuts. That's easy. We can cut this one, and this one, and then this one, and this one. So we make 3 vertical cuts and 2 horizontal cuts, and that's it. But then we want to show that 5 cuts are needed, which means that 4 cuts cannot possibly separate all the points from each other, then why? Okay. And then there are actually two solutions for this one. The first solution is analyze the effect of each cut. So the first cut, without anything, we will create two regions in this plane, okay, on this paper. And now the second cut, with the second cut, it will create two extra regions. And for the third cut, this third cut can cut each of the existing cuts. So in that case, it will create at most 3 extra regions. Why it is at most? Because sometimes we may be cutting at the 3 cuts will be intersecting at the same point. So in that case, we don't have 3 extra regions. But then for the case where no 3 cuts are intersecting at the same point, then we should have 3 extra regions. And for the fourth cut, it will create at most 4 extra regions. So what does that mean? If altogether there are only 4 cuts, then altogether there are going to be 2 plus 2 plus 3 plus 4, 11 regions that can be divided for this paper. Because there are 11 regions and then we have 12 dots. So what does that mean? So it means that for a certain region, it must contain at least 2 dots so that they are not separated from each other. So we are done. But then we have another solution. So this solution, so first of all, this solution cannot be generalized for m points on an n by n grid. Yeah, we can see that it is easily not okay. Let's say when n is equal to 1. So yeah, n is equal to 1 perhaps is okay, but then with for larger m and n, then it is not going to be okay. So the better solution is like this. Okay. So what we are going to do is we ignore actually all the intermediate points inside the outermost boundary of these 12 dots. So when we have a 3 by 4 grid and we join all these boundary points by using straight lines, so we form what? We form a rectangle, right? And this rectangle will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 little edges, 10 segments. But then we see that this is a rectangle and any straight line can cut at most 2 edges, 2 brown edges on this rectangle. Is that okay? So with only 4 cuts, we can only cut 8 edges at most. So that means that there are still some edges that is not cut at all. And in such a case, let's say this edge is not cut at all. What does that mean? It means that these 2 points are all, so this region of the paper is still intact. They are still not separated. So let's say if this edge is not cut, then these 2 points will always stay on the same piece of region. So in such a case, we cannot separate the points from each other. And this solution can be generalized for any m and n. So when we have an m by n grid, then there will be n minus 1 edge here, and there will be n minus 1 edge here. So altogether, there are going to be 2 times bracket of n minus 1 plus n minus 1. So in such a case, we will need at least n minus 1 plus n minus 1 cuts to separate all the points from each other. Okay, yeah, that's all for the solution. Yeah, I hope you understand everything. Yeah, that's all. Okay, so let's see. Okay. Yeah, if you don't have any further question, yeah, let's stop here. And then for next Monday, we will continue with our regular tutorial, yeah, where we are talking about sets, right? So thanks all for coming, and then see you next time. See you next Monday. Thank you very much.